I'm Dr. Ellen Williams. I am a physical scientist, a distinguished University of Maryland professor, and I am a Spartan. My love for chemistry began as a student at Franklin High School in Livonia and grew when I entered Michigan State in 1972 as an alumni distinguished scholar. I was fortunate to have a wonderful advisor, Professor Frederick Horn, who taught me the fundamentals of statistical analysis of spectroscopic signals. Dr. Horn encouraged me to take a graduate-level statistical mechanics class as an undergraduate. The tenets of that class formed the basis of my research ever since. After graduating from Michigan State, I earned a PhD in chemistry from Caltech in 1981. Then it was off to the University of Maryland for postdoc work, where I've spent the majority of my career, the exceptions being the years I spent as chief scientist with BP and then as the director of the U.S. Department of Energy's Advanced Research Projects Agency, Energy. At the beginning of my career, as I was setting up my research lab in Maryland in the early 1980s, I learned of a new instrument that could be used to break new ground in understanding atomic behavior. The scanning tunneling microscope, invented in 1981, offered the ability to capture atomic resolution images. With my research focused on understanding the changes in the surface behavior of atoms and how they are organized in various conditions, being able to capture a three-dimensional image of the surface was a game changer. I knew I needed to have such a microscope and began building one for my lab in 1984. In 1989, I had my first image, which hangs in my kitchen to this day. As an early user of scanning tunneling microscopy, my group was seeing things no one had seen before, because no one had the tool before. It was an exciting time and reinforces how important advances in measurement techniques are to advancing scientific knowledge. Another exciting period in my work came with the explosion of research on the properties of graphene in the early 2000s. Graphene is a single layer of carbon atoms, highly conductive, thin and strong. Its potential as a high-performance, eco-friendly next-generation material excited me. I knew understanding how it behaves in different conditions, how it could be controlled, was going to be important. Today, after years of interdisciplinary research involving theorists and experimentalists, we're seeing the early potential for commercial viability of graphene in conduction and the strengthening of materials nearing reality. Work I did in parallel with my research, consulting on problems for the government, led me to the energy industry and ultimately the directorship of ARPA-E. These roles required a different focus on my part. My scientific background made it possible for me to dig in and understand the complexities involved in issues like nuclear detection and the relationship between climate and energy. Advising in these spaces was a tremendous honor, and it required a measured delivery of easy-to-interpret facts and observations, sanitized of opinions, so policymakers and the general public could make informed decisions from findings they viewed to be credible. I returned to the University of Maryland at the completion of my service to ARPA-E, where I continue to focus on delivering impacts from new scientific knowledge. My work today is focused on identifying new technologies that can slow climate change by reducing greenhouse gas emissions and helping to get them in use as quickly as possible. My advice to Michigan State students is to find what you are most interested in and make it 100% yours. Be the best you can possibly be. Specialize, but at the same time, be prepared to go broader as you follow the pathways that will open for you in the future. Spartans will go beyond the surface.